Right. Hello, everybody. Today you're going to watch me just go through this problem. My AP Stat teacher posted it as a review, and you're going to watch me do it. You're going to watch me make mistakes, and you're going to watch me figure things out in my thought process, okay? We do have the answer key here, so we're going to know if we're doing something wrong or not. And yeah, I'm just going to be, instead of doing it by hand, I'm going to just use, Python to solve this. So let's get started. So construct and label a scatter plot of the data, indicate an appropriate window, and label the axes. So the first thing I want to do actually is import the libraries that we're going to need. So we're going to do pandas for data manipulation, right? So we could have the data frame. We're going to do matplotlib.pyplot. I'm going to import it as a PLT. And we're going to do seaborn as SNS. So those two libraries are going to be used for plotting, graphing, right? We're going to use NumPy for logarithmics, right? Because we're going to be using logs for transformations. And we're going to use SciPy to find the linear regression, or just regressions, right? So we're going to import that as SC. Okay, once you import them, the next thing you want to do is to create your data frame. So the way you do this is you want to set a variable called whatever you want it. I just set it to data frame. And I'm going to use the data frame object or method. From pandas, I'm going to pass in a dictionary, and in quotations, I'm going to add the name of the first column, which is actually toss number right here. It should be here. So that's the X column, if you can think of it that way. So toss number. And then we're going to add a colon, and we're going to pass in a list of those values. So we're going to do 1, 2, 3, 4, 5, 6, 7, and 8. And we're going to skip that first pair, right? We're just going to use from 1 to 8. The next thing we want to do is add the second column. So that's number of dice remaining. And we're going to pass in those values. That's 14, 8, 6, 4, 2, 1, 1, 1. Okay. Arrays must be all the same length. So that means that I didn't add a number. Let's see. So 6, 4, 2, 1, 1, 1, 6. So 14, 8, 6, 4, 2, 1, 1, 1. So it's not that. 1, 2, 3, 4, 5. Okay. Run that, and it should give you your answer. All right. So if you go on to the next line and you call your variable data frame, it's going to give you your data frame and how it looks like, right? So it should be looking exactly like this. Okay. And obviously these are your indices, right? Your index. Okay, so construct and label a scatter plot of the data. So we're going to plot the data. So plot the data on a scatter plot. So the library we're going to use is Seaborn. We're going to do sns.scatterplot. Okay, and inside we're going to pass in the x and y values, basically the values we want to plot. So that's going to be the toss number column in that data frame. And then we're going to do a comma, and we're going to pass in the y value, set that equal to data frame number of dice remaining. Okay, so that's what that looks like. So we can, if we want to describe, actually, let's just follow the examples because I don't want to get ahead of myself. But, it's already labeled with its, it has a scale, and it's labeled, its axes are labeled, okay? It's not number C, part C. Oh, no, part B, excuse me. Perform a linear regression on that data and plot this line on the scatter plot. Okay, so let me add that section. Perform linear regression on data. So the way we're going to do this actually is I'm just going to use sns.regplot. So that's going to plot the data with the regression line. And all I have to do is pass in the same values. So toss number and data frame, number of dice remaining. If I run that, it should give me this plot, so you can see that it's the data, right? But then it has the linear regression, so it has that line basically fitting the data. Okay. Let's see. So the scale is different. So we do have like starting from 2. Here, where's 2? 2 would start like somewhere around here. So it's the same thing, except it's a little bit more up than the original graph. Okay. What's number part C? Part C. Discuss the goodness of fit of. Be sure to include R squared and the residual plot. Okay, so we need to discuss the goodness or how fit this data or this regression line is for this data, like if it's a good fit or if it's not a good fit. So let's go ahead and do so. So let me do that. Part C, discuss the goodness of fit. We're not in GitHub. Okay. So the way we do this is in 3 ways. We want to discuss the R. We want to discuss the R squared, the coefficient of determination, and R is correlation coefficient. And then we also want to do residual plot, because that's going to tell us if the line ultimately really is a good fit. I think R squared and the residual plot helps a lot. So discuss the goodness of fit. So we're going to start by finding the correlation coefficient. Now in your calculator, I mean, you have this whole equation, like not in your calculator, but regularly you have this whole equation, like you have the square root of the sum of, wait, no, that's standard deviation, isn't it? I'm so funny. I think your correlation coefficient, I was like saying the standard deviation equation. The equation for your correlation coefficient, I believe, is like 1 over n minus 1 times the sum of the z-scores, I believe. So like your x initial minus your x mean divided by your standard deviation of x times your y initial minus your y mean divided by the standard deviation of y. I believe that's how it is, but see, in Python, everything is easier, and all we have to do actually is do df.core, so apply this core function to the data frame, and what that's going to output is the correlation, the R, the correlation coefficient of these variables. So if you want to look at toss number, and you want to look at number of dice remaining, the correlation coefficient is negative 0.907265. So if we take that R value, okay, I'm actually going to set that equal to this, right? So that's what R is. If we take that R value and we square it, so in Python, we square by using 2 asterisks. We're gonna set this equal to R squared. So set that value equal to a variable, and then you want to call that value so that it prints, right? Run that, and it should be 0.8231. So if we turn that into a percentage, that's going to end up being what? 82.31%. So what does this value mean? 82.31% of the variability in the number of dice remaining is explained by the least squared regression line that we used in terms of the toss number, that we used on the toss number. So that's good, right? So the more variability that is explained, the more that can be explained by this least squared regression line, the better. Okay, but we have nothing to compare it to yet, but that's the R squared. So I would say that this is a pretty good number, 82.31%. It's okay. Okay. Now we're going to test the residual plot. Now this is really going to tell us if this linear regression is a good fit for this data. So the way we're going to do this is, again, Seaborn, and I believe there is a resid plot. So it's short for residual plot, right? And same thing, you're going to pass in the same parameters. So data frame, toss number, because that's your x, your explanatory variable, and then your y would be your response variable, right? So that would be the number of dice remaining. So in other words, in statistics, you want to say that the toss number explains the number of dice remaining. Okay, so this is the residual plot. Now here is, again, these are some rules about the residual plot. So your residual plot should have no pattern, and your data, or it should be centered around 0. Okay? Well, at least the better. So I'm going to say better fit means that there is no pattern in your residual plot and that it should be centered around 0. Now, what I see a curved pattern. So I can straight away say that, hey, this is not a good fit for the data to predict future values. So what I would say, I was like, okay, I'm not going to use this linear regression because it's not a good fit for the data because it only explains 82%, although it's relative a good number, but relative to some other graphs or some other R-squares, it can be lower, right? So we're going to say not only because it only explains 82.31% of the variability in the number of dice remaining, but because the residual plot has a pattern, a curved pattern, and that's it. Okay, we're going to leave it at that. But usually you can just tell if it has a pattern or not. You don't really need to say should be centered around 0 because sometimes they're not centered around 0, but they don't really have a pattern. But it's overall, it's like spread out evenly. That's what a good residual plot would look like. And we're actually going to see that in a few moments. Okay. So part D, perform the following transformations, exponential and power. Then perform a linear regression for both transformations. So we're going to transform the data to what? To exponential and a power model. So that's part D. Okay. So here is my disclaimer. I only do good on power regressions. For some reason, I struggle with exponential regressions, but let's see if I can strive to get this right for exponential regressions today. So part D, what is it? I'm going to start with transform. Wow, can't spell. Transforming data to a power model. Okay. So the way we start with this is I just like to create a new data frame and just take the log of x and y because we know that the difference between, let me just actually write a little note here. So this is predicted y is equal to my y-intercept plus my slope times my x value, right? So I'm going to say, so it basically predicted y would be equal to a plus bx. Okay, so that's basically what a normal linear regression, least squared regression line would look like, right? When you do a power model, it actually turns to the same base, but you actually have to take the log of the predicted y, and then you also have to take the log of the x, so of your explanatory variable. So you have to take the log of your independent or explanatory variable, and you also have to take the log of your dependent variable, or you could call it your response variable. Okay, there are different names for them. Okay, so that's what a power model is. So let me write it on this like this too. So it's going to be log predicted y, and we're going to say times the log of x here. So that's what the power model is. So that's the transformation that we're doing here. Okay, so we're actually going to use, what are we going to use? SciPy. So we're going to use sc.stats.linregress, right, which we already did, you saw earlier. And we're going to plug in our, what are we plugging in? Toss number, right, and then data frame, number of dice remaining, run that, and it should give you the normal, the least squared regression line for the original graph. So this line that you see right here, this red line, that is your regression line. Let me see if I could change. I'm not sure if I change the color, it's going to change just the line or everything. Yeah, it changes everything. How about, let me Google it. So, how to change, the color of the regression line in Seaborn. How to change the color in Seaborn line. Let's see. Color codes true. Style white. No. Oh, there we go. This is what I want. What is it? Wyatt. What is that? That's interesting. So what is line QWS? Join plot? What? I only think, oh no, never mind. I don't think this works here. Maybe, let's see. I don't think, oh, okay. I could do regline dot set color. Let's see if that works. Let's see if that works. SNS dot regline dot set color. Maybe that doesn't work. Hold on. Is that what it is? Set color red? Yeah, that's not gonna work. Probably with another thing. This is so weird. How about I be specific? In Seaborn dot regplot. Did I already search this up? That's funny. Okay. Oh, okay. Scatter. Oh, so it is. Okay, so I just wanted to make sure that this was an argument that I could even use in the reg plot, because I realized that they had another thing called joint plot or something. I haven't done that yet. So what is it? Line KWS. So I think we pass in a dictionary. I think that's what they gave us. So color kind of reminds me of CSS, like color, black, and quotation marks. So let's do red. Perfect. Okay, so as you can see, right, the red line is your linear regression. And yeah, that's your linear regression. So where was I? Like, I just did a complete pivot to somewhere else. So yeah, so okay, so I was explaining basically what this represents. So this represents the slope of the line we just saw right here. And this represents the y-intercept, right? So when the toss number is 0, basically the number of dice remaining is going to be that number. So it's going to be 12. I'm going to just say 12, right? I'm going to round it to 12. So perfect, right? Okay, so now that we have that, we know already that we determined that this is not a good fit for the data. So we're going to try and see which would be a better fit. Would an exponential model be a better fit? Would a power model be a better fit? We're going to figure it out. We're going to first transform the equation to the data into a power model, and then we're going to see what happens there. So based on this information, I can write my equation. So I can say my predicted y, or we can say my predicted number of dice remaining is going to be equal to the y-intercept, so we're just going to copy that, and then plus the slope times what? Times toss number, I believe it was. That was x. Okay, so this is just for the regular linear regression. So this represents the regular linear regression. We want to transform this into a power model. Again, the way we do that is by multiplying the the independent variable and the dependent variable by log. And you want to make sure it's log 10, right? You don't want to do log base e, you want to do log 10 because you're going to get different answers. And so we're going to go ahead and add that in. So this is basically drafting up an answer. Now here we're going to do the actual coding. So what I just like to copy it here and kind of edit it. So first things first, we cannot do like, it's not math way. We can't just insert certain numbers and expect it to like solve it for us. No, we have to make sure like in a calculator, right? We can't do like, oh, 10y is equal to like 2x plus 2, solve for y. Like you have to move that 10 to the other side. Same thing with Python, we can't have log y, right? So what do we do to cancel out this log on the y side? Well, we know to cancel a log, we can raise it to the 10th power. It cancels out. So that just leaves us with predicted number of dice remaining. So we can delete that part, and right when we do something on one side, we do it on the other. And so we're going to do 10, and again, we square by using double asterisks, and we're going to put everything else in parentheses so that it does its job. Now, let's see. So we have, what is it? Our y-intercept, and then we also have our slope. And then here's the thing, we can't just use log because that doesn't work. Like if you run it, first of all, toss number, did it say to add in a value? I don't think so. Let's just say we want to predict the value for like, I don't know, three toss number. So the number of tosses are 3, and so we want to get the predicted number of dice remaining when we have when we tossed it 3 times already. Okay, not 3 times, I mean what number you got when you tossed it. Wow, Sarai, okay. So what we want to do here is we actually want to use the log function or the log method from NumPy. So we're going to use np.log, and we're not just going to leave it as log. We want to specify log 10 because log and log 10 give you different answers, and we want to do log 10, okay? So now that we have that, this is our actual equation. So this is the predicted number of dice remaining is equal to 10 to the 12 point. In real life, we would just round it like to 4 decimal places, but because we're in Python, I just copied and pasted the entire answer. But we're gonna say like 12.2857 plus negative 1.7024 times the log of 3, right? Because 3 is the toss number we got, and we want to get the predicted number of dice remaining, which we already know what the actual one is. It's actually 6. But let's see what this gives us. Okay. Oh, also, quick thing. Again, it's not math way, so you don't want to use parentheses as to represent multiplication. You just add an asterisk. 1 asterisk is what it represents. So let's cancel that out. What else? np.log. Oh, hold on. And we're not supposed to have spaces in our variables. I haven't made that mistake in a while. So, okay, so now if we call that, it's going to give us our answer. So, wow, that is not a correct answer. So, predicted number of dice remaining if you plug in 3 is that. I doubt it. Okay, so let's see what we did wrong. So, powers, log x, log y. Oh my gosh, it's because, wow, I'm so smart. This is actually, we forgot to actually take the log of x and the log of y. So that's funny. So what we have to do in this case is we have to take the data frame and we have to take the x value. So let's take the x value, and we're going to do is np dot log 10. And I think we can just do this. Instead of doing that, we can just do np.log 10 and do that, and then set that equal to a new data frame called log x. Set that equal to that, should give us the same thing. So now copy and paste that log y and instead add your y variable. So that would be what? Number of dice remaining. Okay, now if you call your data frame, what that's going to do is going to add 2 extra columns to your data frame, so log x, log y. Now you can apply the predicted number of dice remaining using that regression, but I feel like I'm missing something. What am I missing? Okay, so after I transform the data, so this is me transforming the data, this is me getting the linear regression for it. Transform the linear models to exponential and power models using logarithms. Oh, it's not telling me to find the equation. It's telling me to just transform the data and then plot it. Wow, that's interesting of me. That's great, Sarai. That's amazing. But actually, let me check what I did in my previous problem. I think that was day 92. No, maybe it was day 91. Okay, let's see. Yeah, so this is how I plotted. Oh, that's how I plotted it, but it had nothing to do with the actual, with getting the equation. I just did that. Say I did the same thing. Yeah. Weird. Very weird. Okay, so my bad. This is, I feel like this would, my 7th grade teacher, first day of school, he gave us this test and it was like, oh, just try your best or whatever. And it was basically a bunch of equations. And I had this gut feeling of reading the directions. I remember reading it halfway and then just like not finishing because I was like, it's just solving equations. So I just started solving the equations. Turns out, got a 0 because I didn't read the directions because it's set to only solve certain problems, like certain problems that had um like something next to it or something, and I just solved all of the problems, but it didn't count. It was just something, like a little lesson to always read directions. So in this case, I had to read directions. I think I did read them. I don't think I actually comprehended them. So it just says to transform the linear models to exponential and power models using logarithms. So I'm going to delete this. I mean, this is what you are, this is actually the equation for let me see if this is what's wrong with it. This is the actual equation for the power model. But I don't know why it's giving me such a big number. It shouldn't be giving me that number. Oh, wow. It's because obviously I took the this is actually this is the slope and the y-intercept of the original, of the actual regular linear regression line. In order to get the actual slope and intercept for the power model, you would have to do this, right? Pull this function, but instead, what happened? Why did it zoom out? Okay, what is going on? Okay, pull this function, but instead of doing the regular data, you would want to say log x, right? And then you would want to say log y here. And that's going to give you, see, look at us solving our issues. Okay, and then that should be your actual slope. So let me replace that. And then this should be your actual thing. So now, actual y-intercept. So now this makes much more sense. So if we do what? So if we have a toss number of 3, our number of dice remaining is going to be 4. Now our actual is actually 6. So maybe the power model isn't that great. Honestly, so much greater than the first one because That was 294, but that was including like raising it to the 10th power, so whatever. It's okay. But yeah, we don't really need this information. It didn't tell us to create equations. That's just for your own understanding. It just told us to transform it. So I already did transform it. I'm gonna do the same thing now. Let me add data frame. I believe when it's an exponential model, all you have, oh wait, if it's an exponential model, all I have to do is take the log of the dependent variable, or in other words, the response variable, and I already did that. That's log y. So all I have to do now is actually plot the power models. So I'm gonna do plot, not the power models, plot the models. So that's easy for me, because I was like, I thought I had to do like the equation for the exponential, and I feel like that's harder, or maybe it's not harder. Actually, I don't think it's harder. I think the equation, it would be the same thing, except obviously with different slopes. What just went on? It would be the same thing, obviously with a different y-intercept and a different slope, and except it would still have this raised to the 10th power because it would just be the log here, but it wouldn't have this log here. It would just be 3. So I think, oh, wow, I solved my own problem. So this would be predicted number of dice remaining for an exponential model, and this would be for a power model. Do power model. Okay, so there we go. That's a little extra thing for you. So it should give you, actually, I'm kind of interested as to what it's gonna say. Oh, obviously, hold on. Just give me 1 second. I have to actually get. So for that, we would want to get the actual toss number and then get the log y and then substitute these variables. So what is it? Where are we? So here, that would be slope. And then the intercept would be this number here. Let's see what it gives us. Is it literally the exact same thing? That would be funny. Let me see. Oh, it's because this variable doesn't even exist. Remaining power, right? And then this one is going to be exponential. So now, let's start from the beginning. There we go. So now we have, this is what the predicted value of using a power model or a power regression would give us. So that would be 4.0, 0446, right? So 4.0446. And then the predicted value of using an exponential model or exponential regression would be 5.4609. Okay, so you can clearly tell the difference. And then I believe that, did we figure this out for the regular one? I don't think we did. I think we did. Oh, it was like 290 something, but it wasn't the regular one because we still had to do like, we raised it to the 10th power. So let's actually do this. So what was it? The predicted number of dice remaining, and let's do linear and set that equal to what? So it was just regular y-intercept, and then it was what? Plus -1 blah 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 x. So in this case, let's say 3. And I think that's all we have to do. So what's going on? Oops, oops, I always make this mistake. So times 3. Okay. And let me actually call the variable so it prints it out. Okay, 7, right? So we can clearly see that if we actually go to the actual value, it's actually 6. Oh, wow. It's actually 6. Oh, so that's going to tell us something. If this is 7.1, this is 5, and this is 4. Oh, that's very interesting. Which one is actually closer to the actual number of dice remaining, right? So is it going to be, it's obviously not the power one. So is it going to be the exponential one, Or is it going to be the linear one? Let's see, even though the linear one has a curved pattern. So it might not be the best fit. It fits, but it's not the best. But what if the number of dice remaining, I'm sorry, what if the exponential model is like a worse fit, you know? So let's figure that out right now. So I'm actually going to use finally matplotlib. I'm going to do plt.figure. I'm going to create a figure so we can do multiple graphs in one so you could get the idea. I'm going to give the figure a size of what, 2015. 2015, what a year. I was in 5th grade, I think, or 6th, I don't know. Okay, PLD subplot, right? That's gonna create like, I want to do 4. So that means plot 1. So what are we doing? So we're plotting the actual data. So we're gonna just do a normal scatter plot. And I'm actually going to plot all of them now, just so you can see the difference. So this is going to be the regular one. This is going to be the linear one. Number of dice remaining. Then the following is going to be the power one. If you're wondering what this means like 4 rows, 4 columns, and then this is the number 2 in the actual graph, the way it's going to be plotted. We'll see that in 1 second. So this one is going to be what? So we know that the power model is actually you log both of the value of the variables. Also, by the way, if you don't know the terminology, columns, what am I saying? Columns, let me actually, okay, right here. So this is a column, and then this is a row. So rows are horizontal, columns are vertical. And another way to describe a column or to name a column would be either a series or a variable. A statistic is a variable in pandas, it's a series or a column, okay? And then rows are just rows in pandas, but in statistics, they're like instances, cases, accounts, etc. So just because I'm like mixing up terminology here. Okay, so then the next one is going to be a what? A 4 what, third plot? This one's going to be the exponential one. So I believe we keep the x the same. So that's toss number. And then we set the y equal to the log of y. Okay. Plot that. And it should give us the following, right? So this is what the transformations look like. So we have the toss number here. This is the linear one. Let me actually give them titles for you. So I'm going to do plt.title. Wow, really? Cannot spell. Okay, this is the linear model. Not the linear model, I'm going to say original model because it's literally not linear. Original. Okay. And then this one is the plt.title power model. And this one is the plt.title exponential model. Okay. And that's good. I also want to maybe specify a little bit better. So I'm going to label here the x-axis as the log of the toss number, so we know what we're talking about. And then I'm do the same thing. Where else did we do it? We didn't do. So let's do y label for the y-axis. I'm gonna do the same thing for the y-axis, and this is actually the log of the dice or number of dice remaining. Okay. And then I'm gonna do the same thing for this one. I'm just gonna paste it here because it's the actual one that changed. And I think we're good. Log of toss number, log, okay. So yeah, perfect. Okay. Maybe add a space. I kind of like spacing. Okay, better. So this is what the graphs look like. So we have our original model, our power model, and our exponential model. So now, which one actually looks more linear to you? You can actually kind of tell that I'm gonna go with this one. It looks more linear to me. But let's look at their residual plots. I'm kind of like plot the new models on the original scatter plot. You may want to sketch 2 new scatter plots. Okay. Comment on which 3 of the 3 models fit the best. So I'm going to say exponential model just by looking at the graph, right? Because it's more linear than these two, definitely. But let's actually double check. So remember that we checked for the original model if it was a best fit by looking at its correlation coefficient, by looking at its coefficient of determination, and also by looking at the residual plot. So we're going to do the exact same thing for all of these. So we already did it for the original model. So let me go ahead and go scroll up and find that. So let me just copy and paste this. Okay. Paste that in there. So let's just go over it really quickly. So if we're talking about the R of the the original model, we had a negative 0.907265 correlation coefficient, meaning the toss number and the number of dice remaining had a strong negative, a strong negative, well, a strong negative correlation. So they were, yeah, we're gonna just go with that. Okay. R squared, meaning the coefficient of determination, meaning that it 82.31% of the variability in the number of dice remaining is explained by the least squared regression line that we used on that model. And the residual plot looked like this. So it had a pattern. It's very curved. So because of that, we said it wasn't a good fit. But it's not a good fit, but it might be better than another one, or it might be worse than another one. So we're going to do the same thing for the other one. So I'm going to go ahead and specify. So this is the original model. Next is going to be what? The power model. So I'm just going to find the values of everything first, and then we're going to go back and we're going to compare them. Okay, so df.core once again. This time we have our new variables. So what are we doing? So for the power model, I remember it's just log x log y. So this is the correlation coefficient of the power model. So I'm going to say R power is equal to that value. Now that I think of it, I kind of want to go back and instead of saying linear, where is it? Power exponential linear. Instead of saying linear, I just want to say like original. I think that's a better description. Or original, because it wasn't linear. The graph wasn't original. That was going to give me an error. Okay, let's go back. So where were we? So this is our power, the correlation coefficient of the power function. Okay, now let's look at R squared and what that is. All we have to do is legit just square R. So that's going to end up being R squared for our power model is going to be equal to literally R squared. So let's run that so we actually get the answer. So, okay, that's pretty good. So what is that? That's like 82.31%. Okay. Pretty sure that's the same thing. Oh, wow. It is the same thing. So now let's look at the residual plot. So I'm going to do SNS.residPlot. What is it? So it's going to be x is equal to data frame log x. And then y is equal to data frame log y. Oops. Okay, nope. Again, oops. There we go. Run that. Okay, so this is our residual plot. So I'm just going to leave that there. We're going to come back to it. Let me get the exponential model stuff done now. So exponential model. So again, we're going to find what R is. So I don't really have to do this again. I could just scroll back up, but just for the sake of this. So again, we leave x the same for an exponential model, and the only thing we do is log the y, I believe. So it's going to be log y, and then number of dice remaining. Nope, that's y. Log y, and then keep the x the same. So that's the correlation coefficient. So I'm going to set r equal to that value, and then I'm going to go here and I'm going to take r squared exponential, set that equal to, oh, hold on. I want this to be r. Oh, now I know why it's the same thing, because I didn't specify our power. There we go. So much better. Can't believe I made that mistake, but it's okay. Mistakes are good. You learn from them. So, because I was like, I want to name this. So exponential, there we go. Now we can take our r exponential, square that. I was like, that doesn't make sense for it to be the same thing. Nope. Okay. So r squared exponential, run that. Okay, so that's what? 94.63%. Okay, that's good. Now let's do a resid plot so we can compare residuals. So let's do what? So our x again stayed the same, and the only thing that changed was that we logged the y for an exponential model. So log y. Okay. All right. Okay, so now what I want to do is I want to compare all these values. So the first thing I'm going to do is actually, I want to show it to you graphically. So I'm going to say comparison. So this is basically part G, right? We are comparing residual plots and analyzing, our r's and our r squares. Okay, so comparing residual plots. So what I'm going to do is I'm going to plot this in a figure once again. You know what? I can just go back up. I'm just going to copy this, go back down, paste it. And instead of saying 4, 4, 1, I'm going to do 6, 6, 1. Change that to 6, 6, 2, and 6, 6, 3. And then I'm going to do another one, subplot 6, 6, 4. And this one's actually going to be the residual plot of the original model. So we're going to paste that in there. And then going to do this 2 more times. Down here, change the numbers 5, change the numbers 6, and then copy the residual plot for the power model. Paste that as the 5th plot, and then finally copy the residual plot of the exponential model. Paste that as the 6th plot. Run it, and it should give you 6 graphs. Okay, that's great. So they're a little too small for my liking. So how about instead of doing 6 columns, we do 3 columns? And I think that should make the 3 graphs go to another row. Did I mess up? Yeah. Okay, right here. Huh, weird. I mean, it did work, but they're different sizes. Why are they different sizes? The original model, power model, exponential model. It's okay. I think we got the same thing. It's the same. It gets the idea done. They don't have to be perfect. So, let me just fix the axes for these. So let's see. So this one's original model, doesn't need anything. So the power model, I'm going to go ahead and add the same labels there. And then this one also add the same labels there. Run that. Let me actually do full screen. Okay, so after doing this, you can finally see, let me actually zoom in a little bit. Okay, so now let's do a comparison. So this is the original model, this is the residual plot of the original model. This is the power model, this is the residual plot of the power model. This is the exponential model, and this is the residual plot of the toss number. Of the toss number, please, of the exponential model. Okay, hold on, just want to make this a little bit bigger. Because they're like overlapping each other. Okay, perfect. So if we take a comparison, if we do a comparison here, oh, I thought that was like a marker thing, never mind. What is going on? What is that? What did I just do? Let's get out of here. Okay, so you can clearly see that this one has a curved pattern, right? So the original model has a curved pattern in its residual. And this one has a curved pattern also in its residual, and the only one who doesn't, who's kind of the most randomly placed, is actually this one. This is the one that's most randomly, evenly spread out. It's centered around 0. Like here you see that these ones are like very low, these ones are like very high, and then like weird here. These are mostly centered around 0, besides like these two here. You can see that the actual data is legit linear, right? Here it's curved, and so what further supports that the exponential model, by the way, if you haven't noticed yet, the exponential model is the better fit for this data, but what further supports the exponential model being a better fit is its determination coefficient, or the coefficient of determination, which is your r squared. So if you take a look at them, I'm going to create a data frame for you just so you could see it. So I'm going to create this r squared equal to pd dot data frame. I'm going to do, what am I going to do? So model, I'm going to do what? So original, power. Okay, perfect. So here's my little table. So this is the model, this is the r squared in percentage. So the original model had, 82.31% of the variation of the number of dice remaining was explained by the least squared regression line used in the toss number. So the least squared regression line we use in the toss number was, the original one, the normal one, right? So then we transferred the data to a power model, and 91.73% of the variation of the number of dice remaining was explained by the least squared regression line that we used in terms of on the toss number. So remember, the least squared regression line that we use on the toss number, if we go and scroll up, is where is it? Is this one, right? So this is the one we use for the power. This is the least squared regression line we use for the exponential exponential model, and then somewhere up here, right, this is the least squared regression line that we use for the original model. Okay, so that's what we're talking about. And then finally, for the exponential model, 94.63% of the variation of the number of dice remaining was explained by the least squared regression line used in that model, which is the exponential regression, right? So we can say now the exponential model is the best fit for our data because not only is the relationship between the toss number and the log of the number of dice remaining is more linear, gonna say fairly linear is fairly linear, but its residual plot shows no pattern, and it explains, and the model explains the model explains 94.63% of the variation of the number of dice remaining, explained by the least squared regression line, the LSRL, on the toss number. So yeah, I think that's a good explanation. So basically, I think if you are going to be confused, you might be confused on this part here. So 94, the model, it doesn't, we could say shows 94.63% of the variation, or we could say, and, well, no, yeah, and the model shows 94.63% of the variation of the number of dice remaining explained by the least squared regression line on the toss number. So we're pretty much talking about the LSRL. We're not talking about the model. So let me delete that. We're gonna say the linear. Well, we can say that, I don't even know. So I'm just gonna leave it like that. 94.63%. Oh, I should write and 94.63% of the variation of the number of dice remaining is explained by the least squared regression line on the toss number. So I don't think that makes sense. On the toss number performed, that was used, or in terms of the toss number of the toss number. Okay, so the exponential model is the best fit for our data because not only is the relationship between the toss number and the log of the number of dice remaining is fairly linear, but its residual plot shows no pattern, and 94.63% of the variation of the number of dice remaining is explained by the least squared regression line in terms of the toss number. Final answer is that the exponential model is the best fit for our data. Okay. So, yeah, so this is the graphing comparisons. Did I miss anything? I think we got everything really right. This is her doing it like, let me just check our numbers. So for the first one, what is it? So for the first one, ln-reg of L1 versus L4. So that's going to be what? I think that's the exponential because that's normal x and then log of y. So yeah, that's exponential. So it should be, that's our R's. Okay, so I was like, what? That's not what I got. Yeah, that's because that's our R's, not our slope and intercepts, all right. Okay, so yeah, makes sense. So this is our 0.186. So we got 0.18. Wow, did I say 86? I mean 0.1806. So that's right here. Good. 1.2792. That's right here. Good. So next is our, that's still the exponential. This is our, I believe, okay, this is our power model, right? So that is 1.2833, 1.27, where is it? Yeah, 1.2873, that's our power model. And then 1.426, perfect. Okay, so that's right. And she didn't do the linear one. Well, obviously the linear one is just self-explanatory, I think. I mean, I think I would say so because that's the calculator even gives it to you. But yeah, so that's credibility, just sorry. Credibility, so you know that this is all correct. Yeah, so if you have any questions, let me know. The final answer was that the exponential model was the better model to perform a least squared regression line. Okay? If you have any questions, let me know. Have a great day.